According to Bohr's model, which of the following wavelengths will not be absorbed by an electron in the first orbit? A. 142 nanometers, B. 122 nanometers, C. 97.5 nanometers, or D. 94.0 nanometers. According to Bohr, the energy of an electron in the nth orbit of hydrogen is negative 13.6 electron volts divided by the square of n. An atom will absorb electromagnetic radiation if the energy of the photon is equal to the energy gap between two allowed orbits. Let's calculate the energy of a photon that would excite an electron from the first orbit to the second orbit. The energy of the photon will be equal to the energy of the electron if it were in the second orbit, minus the energy of the electron in the first orbit. The energy of the electron in the second orbit is negative 13.6 electron volts divided by 2 squared, and the energy of the electron in the first orbit is negative 13.6 electron volts divided by 1 squared. This gives us a value of 10.2 electron volts for the energy of the photon. We can convert this to joules. Our conversion factor here is based on 1 electron volt being equivalent to 1.6 times 10 to the negative 19th joules. 10.2 electron volts times 1.60 times 10 to the negative 19th joules over 1 electron volt equals 1.63 times 10 to the negative 18th joules. Now that we have the energy of the photon, we can calculate the wavelength. The energy of a photon is related to its wavelength according to the equation E equals h times c divided by the wavelength lambda. In this equation, h is Planck's constant, which has a value of 6.63 times 10 to the negative 34th joule second, and c is the speed of light, which is 3.00 times 10 to the 8th meters per second. We can rearrange the equation to solve for lambda. Lambda equals h times c divided by the photon energy. This gives us a wavelength of 1.22 times 10 to the negative 7th meters, or 122 nanometers. Therefore, choice B, 122 nanometers, will be absorbed by the electron. Since 122 nanometers will be absorbed, choice B is not the correct answer. We're looking for the wavelength that will not be absorbed. We expect transitions to higher orbits to involve higher photon energies and shorter wavelengths. Since choice A, 142 nanometers, is the only wavelength longer than 122 nanometers, we can be sure that it will not be absorbed. The correct answer is then A. If you want to convince yourself, you can do a similar calculation for the transition to the third orbit. You should find that a shorter wavelength of 103 nanometers will be required. If you calculate wavelengths for transitions to even higher orbits, these are what you'll find. You will note that choice C, 97.5 nanometers, will promote an electron from orbit 1 to orbit 4, and choice D, 94.0 nanometers, will promote an electron from orbit 1 to orbit 5. The required wavelengths get shorter, but you will find that the numbers will converge to 91.4 nanometers. That's because the gaps between adjacent orbits become smaller and smaller as n increases. This entire series of wavelengths are experimentally observed and is known as the Lyman series. Bohr's model attributes these to transitions to or from the first orbit.